Hello everyone, my name is DJ. Welcome to my course. Today we're gonna cover CHE1501 General Chemistry. What's under the course? What is covered in this course? There are essentially 11 units. So the first unit is Chemical Foundations. Chemical Foundations. Unit 2, Quantum Mechanics and Periodicity. Unit 3, Chemical Bonding and Bonding Theories. Unit 4, Types of Chemical Reactions. Unit 5, Stoichiometry. Unit 6, Solutions and Expression of Concentration. Unit 7, Introduction to Kinetics. Unit 8, Chemical Equilibrium. Unit 9, Acid-Base Equilibria. Unit 10, Introduction to Thermochemistry. Unit 11, Gases. So basically these are the 11 units we shall cover in this course. So how are we gonna be tackling this course? In each unit we'll cover the theories that are associated with this course. For example, in Unit 1 we'll cover Chemical Foundation. So there will be several subsections in each unit. We shall discuss the theory, giving examples where appropriate, and covering all the necessary knowledge that you need to have for this course. For advanced content, which shall be covered in a different course, that one will be covering tutorials, which will be an extensive course on tutorials and exam. So basically this course will give you a general knowledge, which is the minimum that you need in order to pass this course. But if you need to go an extra mile, there's another course for tutorials and exams. So we'll be looking at previous exams and intensive examination of how questions are asked and so forth. So if you need that extra, you are also encouraged to purchase that course. So let's move on to Unit 1. Unit 1, Chemical Foundations. So the first subsection is Atomic Theory. The concept of atoms play a fundamental role in chemistry and is formalized by the modern atomic theory, first stated by John Dalton, an English scientist, in 1808. It consists of 3 parts. So these 3 parts, they form the foundation of the chemistry that we shall cover in this course and all chemistry in general. So the first part is all matter is composed of atoms. Whatever you think of, wood, metal, bread, everything is composed of atoms. Then 2, atoms of the same element are the same. Atoms of different elements are different. So what do we mean by this? If we talk of hydrogen, denoted by an H, all hydrogens are the same. There's no different hydrogen. They are the same. And the other element can be carbon. So hydrogen and carbon, they are different. So different atoms are different. Just like apples are different from oranges. So number 3, atoms combine in whole number ratios to form compounds. So for example, if you talk of maybe water is H2O, 2 hydrogens and 1 oxygen. It means the formation of water, it requires 2 hydrogen and 1 oxygen. You cannot say I'm gonna have half water. No, it must be in whole number ratios. So when the elements are combining, you cannot say I'm taking half hydrogen and a quarter of oxygen to form a certain compound. No, they must be in whole number ratios, which means 1, 2, 3, 4, 5. It's not 1.5 or 1 1/4 or 3.8. There are no fractions when you are talking of atomic theory. So whole number, ratios. So these three are the basics that you need to know for the atomic theory that shall be based on all things that we shall cover. So all matter is composed of atoms. Atoms of the same element are the same, and atoms of different elements are different, and atoms combine in whole number ratios to form compound. These concepts form the basis of chemistry. So let's move on. Atoms, elements, compounds, and molecules. Atom is the smallest unit of matter that can take part in a chemical reaction and which cannot be broken down chemically into anything simpler. So an atom is the smallest unit of matter, which means there is nothing smaller than an atom. Element is any substance made of the same atoms. So we can have an hydrogen element, carbon element, so they are the same element, hydrogen, carbon, same element. Then compound is a substance made of two or more elements. So when you talk of water, the example we gave earlier is H2O, two hydrogens and one. So there are two different elements, hydrogen and oxygen, forming a compound. And there is sodium chloride, which is Na for sodium, Nl for chlorine, so it's sodium chloride. So this is your table salt. So it's sodium and chloride. So this is a compound because it's two different elements. Molecules is a group of two or more atoms bonded together. Therefore, we can have molecules of elements or molecules of compounds. So what we mean, hydrogen, it combines with another hydrogen to form hydrogen, maybe let's say hydrogen gas. So hydrogen gas is a molecule, but it's a molecule of the same elements. Then there can be molecules of compound, which is like this one, water molecule. That's what we mean, molecules of element and molecules of compound. Compound is just two different elements that are joined together to form a molecule. So like water, H2O is a water molecule, and hydrogen gas molecule, or hydrogen liquid, or depending, remember the state of matter, the temperature determines the state of matter. So water, it can also be a gas, liquid, and a solid. Ice at 0 degrees, gas at 100 degrees, at normal room temperature is liquid. But the basic thing is there are molecules of elements and molecules of compounds. So these are the things you should know. So just know that an atom is the smallest unit of matter, and there are elements, which means it's the same atoms. Then compounds is two different atoms. So let's move on. 6. So we talked of atom, molecule, and compound. So here we are looking at what it is, which is the definition, and the differences, which means the differences as compared to these three aspects. So for an atom, the definition is fundamental building blocks of life, a collection of protons and neutrons surrounded by a cloud of electrons. So this is another alternative definition. Then the difference, atoms are the thing that make up molecules and compounds. So atoms, they are constituted in these, because these ones, they use atoms to form a molecule or compound. So now, molecule, two or more atoms are joined together with covalent bonds. Difference, molecules contain two or more atoms and are held together by covalent bonds, whereas compounds are held together by ionic bonds. So these are ionic and covalent bonds. They are covered in the units that are going to come, but for now, just to give you an appetizer. So covalent bonds, they are formed using electrons. So it means, let's say hydrogen it's got one electron and there's another hydrogen. So they combine their electrons to form a covalent bond. So covalent bonds are made by sharing electrons. Then ionic bonds are based on the charge. For example, sodium chloride. Sodium has got one electron, it loses it and it gains a positive charge. Then chlorine, it takes that electron, then it gains a negative charge. So the positive and negative charge, they form the ionic bond. So if you ask the difference between a molecule and a compound, you say molecules, they are formed by covalent bonds. Then compounds that are formed by electronic, ionic attraction, which means positive and negative charge. Then the other difference is molecules can be formed by the same element. For example, a hydrogen molecule, same element, or two or more different elements, like this. Then, but compounds, they are different elements only, different elements. So these are the two many differences that you can have. So compound, two or more elements bonding together through ionic attraction. Compounds contain two or more atoms and are held together by ionic bonds, whereas molecules are held together by covalent bonds. The atoms within a compound must be different from each other, whereas a molecule can consist of only one element. But expanding from what we have discussed earlier, you should add here or different elements like a water molecule. Structure of the atom. The atom consists of positively charged nucleus consisting of proton as a positive charge and then neutrons with neutral charge. So neutron. So remember that when you see neutrons, just know that they have no charge. That is surrounded by a cloud of electrons with a negative charge. Chemical properties of an element are determined by the charge of its nucleus. That is determined by the number of protons in the nucleus, denoted by the letters Z or Z, also known as atomic number. The atomic mass number, denoted by A, is the total number of protons and neutrons. The mass of an atom depends on how many nucleons its nucleus contains. So let's say I've got an atom. So this will be the nucleus. So in the nucleus, you can have, let's say, this is a protons, and let's give another color, and let's say these are neutrons. So basically, what we are saying, the nucleus, which is the center, it is composed of protons and neutrons. So these protons and neutrons, they form the nucleus. So they are collectively called nucleons. So the reason why the nucleus has got a positive charge is because the neutrons, they don't have any charge, but the protons, they've got a charge. So since they are the only charge items there, the nucleus therefore has a positive charge. So, but at the shell or the cloud, there are, okay, let me use a different color here, let's say blue. There are electrons. So electrons, they've got a negative charge. So they balance out the nucleus. So basically that is it. The nucleus has got neutrons and protons, which are collectively known as nucleons. Remember that. And the outer shell or the cloud has got electrons. So electrons are not inside the nucleus. They are in the shells. You shall understand it better in the units that are to come when we discuss it more. So just know that the atomic mass number is the total protons and electrons. So let's move on. So basically, if you look at your periodic table, let's give example carbon. Carbon is represented by C, which is the chemical symbol. Then 12 will be the atomic mass number. Then 6 is the number of protons. So basically what we are saying the atomic mass number is the number of nucleons, which means it's protons plus neutrons, which give you 12. So basically, if you want to find the number of neutrons, you already know that 6 here, representing the protons, is here, and the total is 12. So that's why if you want to find the number of neutrons, you say N is equals to A minus C. So in this case, A is 12. Then your Z, number of protons, is 6. So it gives you 6 neutrons. So that's how we use it. So for each element, if you look at your periodic table, you will see this symbol. So just know that A, atomic mass number, number of protons. So let's move on. So here is an illustration of a carbon atom. So the nucleus has got 6 protons and 6 neutrons, and this one represents the electrons, so it's 6 electrons. So the first shell has got 2 electrons, the second shell has got 4. So basically this is how an illustration of an carbon atom. Isotopes. Isotopes are various forms of an element that have the same number of protons, but a different number of neutrons. Some elements such as carbon, potassium, uranium, and have multiple naturally occurring isotopes. Isotopes are identified first by the element and then by the sum of protons and neutrons present. For example, carbon 12. Carbon is the element and 12 is the sum of protons and neutrons. So when you say carbon 12, it means it contains 6 protons, 6 neutrons. So 6 plus 6 and 6 electrons. Therefore, it has a mass number of 12. 6 protons plus 6 neutrons. But the other version of carbon is carbon 14. It means it has got 6 protons and 8 neutrons. So remember, when you write it now, carbon 12 will be 12, 6 like this. Then carbon 14 will be like this. So to get the number of neutrons, remember with this formula, N is equals to A minus C. So for here, you just say, like we did previously, 12 minus 6 is equals to 6 neutrons. For the other one, it will be 14 minus 6. Then you get 8 neutrons. So if you go back to this, so remember this formula is quite important. And remember, this is always the number of neutrons. Okay. I think that's so. Isotopes, you can view them as twins. They can be identical twins but with different characteristics. So in this case, the different characteristics are the number of neutrons. So isotopes are various forms of an element that have the same number of protons but a different number of neutrons. So you must remember that isotopes are important. Carbon 12, carbon 14. Okay, let's move to the next subsection, units of measurement. Every field of science involves taking measurements, understanding them, and communicating them to others. In other words, we all have to speak the same basic language. Whether you are a chemist, a physicist, a biologist, an engineer, or a medical doctor, you need a consistent way of communicating size, mass, shape, temperature, time, amount, energy, power, and speed. In this regard, International System of Units, also known as SI units, is the metric system used in science, industry, and medicine. So scientists, so that different challenges in communicating measurements. So they developed what they call SI system of units, which are the standard units used throughout the world. So let me give you an example. NASA 99 rocket launch failure. NASA lost 125 million Mars climate orbiter because of spacecraft engineers failed to convert English to metric measurements when changing vital data before craft was launched. So basically there were two groups of companies which were working together in the development of a spacecraft. So the other group was using metric units and other one was using English units. So basically we are saying a navigation team at Jet Propulsion Laboratory used metric system, which are millimeters and meters, in its calculations, whilst Lockheed Martin Astronautics in Denver, which designed and built the spacecraft, provided crucial acceleration data in the English system, which are inches, feet, and pound. So now when this other calculation was saying 2, maybe it referred to 2 meters, and the other one thought that it was 2 feet. So now it disturbed or distorted the calculations which were needed to send that rocket into an orbit. So by virtue of using different units, it confused the calculations and caused the rocket to fail. So this illustrates the importance of using SI units so that there won't be confusion between what you say. For example, if you go to America and you say, how much do you weigh? They can tell you 200. They'll say 200. But because we are in South Africa, you use kgs. When someone is weigh 200 kgs, too much. But 200 pounds in America, it's much less than that, than the 200 kg. So you have to use SI units so that we avoid such confusion. So let's move on. SI units, there are 7 base units for the SI system. So for kilograms, we use it for mass. Seconds, we use it for time. Kelvin, we use it for temperature. Ampere, or commonly shortened as amps, we use it for electric current. And more, we use it for the amount of substance. Then candela is used for luminous intensity, which has to do with the brightness. Then meter, we use it for distance. So you can see the abbreviations. These are the like the shortens. Instead of saying kilogram, you can just say kg. Then S for second, K for Kelvin, A for ampere, then MOL for mole, CD for candela, and M for meter. So these are the common shorthands that are used. For example, Kelvin there is the SI unit for temperature, but we often use degrees Celsius, and in America they use Fahrenheit. But when you are doing standardized things, you should use Kelvin. So these are some of the confusion that can happen if you do not use SI units. So remember, these are the 7 SI units. You should remember them, and they are examinable. Let's move to the next subsection, uncertainty of measurement. The uncertainty of a measurement tells us something about its quality, precision, and accuracy. Precision measures the closeness of repeated measurements to one another, whilst accuracy is the closeness of a single measurement to its true value. So basically, let me give you an example. Let's say you've got a bull's eye, or you're playing darts. So this is the middle, the bull's eye. So if you are talking of precision, it means if you throw maybe 3 darts, if you hit maybe here, you can say you are precise. But your main target is the bull's eye. So you are precise, but you are not accurate, because your darts are falling near to each other. with each throw that you make, they are close to each other, but they are far away from the target, or they are not at the target. So you are precise but not accurate. But you can be precise also and away from the target. Like here, your darts can fall here. You are precise because you are repeating the same position, almost the same position. So you are a bit precise. Then the other one is accuracy. So accuracy is how close you are to the target or to the true value. So maybe the true value, let's say it's the bullseye. So these two, they are precise, but this one is more accurate because the distance is shorter here than as compared to this one. So then the other example would be like, you might not be precise in the case, let's say the first throw is here, the other one is here, then the other one is here. So in this case, we can say you are not precise. You understand what I mean? So you cannot be precise as well, but yet you are accurate. So let me draw here to avoid confusion. Okay, choose maybe green. So you can maybe one dot is here, one dot is here, one dot is here. So we can say you are accurate because your dots are close to the bullseye, to the true value that you are supposed to get, but you are not precise because the dots are not close to each other, which means they are each time you are aiming a different position. But let me give another one. So let's say you throw here, almost the same position. So you can say you are precise and accurate. So precision has to do with the closeness of repeated measurement, which means you're getting the same position all the time. Then accuracy is your closeness to the required value. Okay, let's move on to the next point. Uncertainty of measurement is the doubt that exists about the result of any measurement. You might think that well-made rulers, clocks, thermometers should be trustworthy and give the right results. But for every measurement, even the most careful, there is always a margin of doubt. In every speech, in everyday speech, this might be expressed as give or take. A stick might be 2 meters long, give or take, which means there is a margin of error. So, for example, when you are using maybe a tape measure, the margin of error can be plus or minus a millimeter, for example. So if you maybe use a stopwatch or a stop clock, some are precise. The margin of error can be a second, can be a second or a millisecond, depending on the make of the clock that you are using. So the take-home point here is precision. It has to do with are you able to repeat? Then accuracy has to do with the closeness to the true value. So for example, let's say this pen, let's say is 15 centimeters, for example, the actual. So if you use a tape measure, it can give you maybe 15.2. If you use another type of measuring device, you can get 14.8. So now the margin of error can be different from measuring device to another. So that's why in the industry they want you to calibrate. Calibrate is when you use an instrument, with time it can give you different results which may not be accurate. So you need to calibrate to make sure that your measuring device, they are still measuring whatever you want to measure accurately. that is under the quality department. Okay, let's move on. So why uncertainty of measurement is important? Uncertainty of measurement, let me just delete that first. Why uncertainty of measurement is important? You may be interested in uncertainty simply because you wish to make good quality measurements and to understand the results. However, there are other more particular reasons for thinking about measurement uncertainty. You may be thinking or making the measurement as part of a calibration, like what I was telling you earlier, that calibration is required as part of industry standards, that your thermometers, your measuring device for length, it must be calibrated so that you ensure that you are making accurate readings or results. Then you can need to know uncertainty of measurement because you want to test. So second, test where the uncertainty of measurement is needed to determine a pass. So for example, you might say for a particular, maybe you are manufacturing spare parts. So in order for that spare part to fit into the device, maybe a car part, to fit in a certain, to work as a spare, it needs to meet some certain measurement criteria. For example, if it's a bolt, if you want to put it on a certain part in a car engine or something like that, if it's too big, it will be loose. If it's too small, it won't fit. So it has to be under a certain level of uncertainty so that it can pass, to be acceptable. Tolerance is where you need to know the uncertainty before you can decide whether the tolerance is met. So tolerance is also applicable to the previous point, to say maybe, let's say you need a 5mm bolt. But tolerance, maybe you can say a tolerance of 2mm, which means from 4 millimeters to 5.2 millimeters. So it means this range, you accept it. So that is part of the test, and tolerance, that is part of which range is acceptable. So measurement is done for 3 reasons: calibration, testing, and tolerance, to know the specs of a device. Okay, moving to the next. So measure thrice, cut once. So what it basically means, it means when you are doing your measurements, you must be sure. It's better to measure more than once so that you can ensure that the result that you got is the same. So you can reduce the risk of making a mistake by checking the measurement a second time or a third time. That's why maybe you can do the measurement, then the quality control comes and checks. This is one aspect of reducing making mistakes. Then where do errors and uncertainty come from? Flaws in measurement may be visible or invisible, because real measurements are never made under perfect conditions. Errors and uncertainty come from, number one, measuring instrument, which means the instrument you are using might be having some flaws. Instrument can suffer from errors including bias, changes due to aging, wear, or other kind of drift, poor readability, noise for electrical instrument, and many other problems. So when we say poor readability, it means maybe if it's a ruler, maybe the marks, the demarcations are fading. So by reason of that, it can make you make measurement errors. Instead of maybe you reading the correct measurement, because of the fading, you can misread it, which can cause measuring errors. Then number two, items being measured, which may not be stable. Imagine trying to measure the size of an ice cube in a warm room. So it means the ice is constantly changing size because it's melting. So the item being measured, it might not be stable. And number 3, measurement process. The measurement itself may be difficult to make. For example, measuring the weight of a small but lively animal presents particular difficulties in getting the subject to cooperate. Let's say you want to measure maybe the weight of a fly. How can you do it? It cannot cooperate with you. So the thing that you're trying to measure might not be cooperating. So that is the error that can come due to the measuring process. So there is important uncertainty. So calibration of your instrument is an uncertainty which is then built into the uncertainty of instruments you make. But remember that the uncertainty due to calibration will be much worse. So let's say your ruler you are using, your measuring instrument, has got an error. Maybe it adds maybe 5 millimeter in each measurement. So maybe you are measuring something that is maybe 50 millimeters. So instead of it giving you 50, it gives you 55 millimeter. So by making maybe having several parts, so it means each part that you are measuring, you are adding 5 millimeters, so it can compound. Let's say maybe you are supposed to join 2 rods. Let me give a rod. So it means if you join 2 rods, you now have an error of 10 millimeter, which can compound now as you add more items. So important uncertainty, calibration of your instrument is an uncertainty which is then built into the uncertainty of the measurements you make. So it means if your instrument, the ruler, is making wrong measurements before you even start measuring, it means it's the uncertainty brought by the calibration, which means it's measuring wrong readings plus your own human errors, which are the process of measuring and the items being measured may be unstable. So it means in addition to the error of the instrument being used to measure plus your own human error, it makes it worse. So remember these 4 errors. Significant figures. The number of significant figures refers to the number of digits reported for a given measurement. The greater the number of significant figures, the greater the precision of the measurement. So if we say 2 significant figures, we mean it must have 2 digits. Significant figures. The number of significant figures refers to the number of digits reported for a given measurement. The greater the number of significant figures, the greater the precision of the measurement. There are 3 rules for determining how many significant figures are in a number. Non-zero digits are always significant. Non-zero digits are always significant. Any zeros between 2 significant figures are significant. Any final zero or a trailing zero in a decimal portion only are significant. Any final zero or a trailing zeros in the decimal portion are only significant. So when you say non-zero, okay, let's give like 5, 0, 0, 1, 0.2, 0, 0, 0, 5. So what we are saying, any non-zero digits are always significant, which means any number which is not 0 is significant. Any zeros between 2 significant digits are significant. So these are non-zeros. Okay, let me use a different color. Okay, what am I doing now? Okay, let me screen. So here is a non-zero. So these 2 are significant. And any zeros between two significant digits are significant, which means these two zeros are significant because they are acting as placeholders. So if you remove these zeros, it's no longer 5001.20005. It becomes 51. So they are significant because they are placeholders. Then any zero, a final zero or a trailing zeros in the decimal portion only are significant. So these are trailing zeros because after the comma they are acting as placeholders. So a final zero or a trailing zero in the decimal portion only are significant. Math with significant figures. Exact numbers such as the number of students in a class have an infinite number of significant figures, as they are not measurements made with instrument. Therefore, if a number is exact, it doesn't affect the accuracy of a calculation nor the precision of the expression. So if you are counting numbers in terms of which are not measured by measuring instrument, it means the significance is infinite because there is no accuracy attached to any measurement. Like maybe you are using a scale, maybe the scale might be having some errors or something of some sort, but since you are counting, there is no errors in counting. I don't know how much more I can make it plainer than that. So we are basically saying, because we are saying, okay, let me take a pen. So if you say 1, 2, these are 2 pens. So there cannot be any measuring error because we already know that it's accurate that these are 2. So basically, what we are saying, exact numbers such as number of students in a class have an infinite number of significant figures, as they are not measurements made with instruments. So it means the accuracy, it cannot be limited to a particular decimal number or a particular significant figure, because there is no errors that can be made. So because significant figures, they mainly are correlated to the accuracy or a tolerance that an instrument can give. For example, if you are using a ruler, normal ruler, maybe then the significance can be limited to the nearest millimeter. So if you are maybe measuring in maybe centimeters, so it can be limited maybe to the nearest let's say it's 50.1. So the significance may be 3 figures, because maybe I'm measuring in millimeters or something like that. Such as the number of students in a class have an infinite number of significant figures, as they are not measurements made with instruments. So if you are not using instruments, the significance is infinite. Therefore, if a number is exact, it doesn't affect the accuracy of calculation or the precision of the expression. Addition, subtraction, multiplication, division involving significant figures, the answer is reported in such a way that it reflects the reliability of the least precise operation. So, for example, let's say, let me draw a rectangle here. Let's say use different measuring instrument to measure the length. So you measure the length here, maybe you get 10 centimeters. Then you use another measuring instrument, and this side you get 5.0 centimeters. So it means if you are asked to calculate the area, it's 10 times 5, which is 50.0. That's what most people do, square centimeters. But now, according to the laws of the significant figures, you only use the least precise, which means 5.0 is precise because you used a more precise measuring instrument. But now the 10 centimeters, you used a least because it cannot go to decimal place. So it means when you're giving your final answer, you should be using the least precise, which means the one which is less accurate. So the correct answer will be 50 square without the decimal place. So that's what we mean here. So we'll give you an example. So 2.5 times 3.42. The answer to this problem will be 8.6, which was rounded from the calculator reading of 8.55. So since 2.5 is the least precise reading, because 3.42 is more precise because it gives you extra decimal place. So you use the less precise one. So your answer should be to the nearest, like the one decimal place. So which is 8.6. 2.5 has two significant figures, while 3.42 is 3. The two significant figures is less precise than 3, so the answer is two significant figures. So that's another way of saying it, but it's just the same thing like what I was saying. So let's move on to the next, dimensional analysis. So dimensional analysis is the art of converting from one unit to the other. Let's say you want to convert pounds for weight into kgs. So dimensional analysis is the relationship between different measuring units. So it involves using conversion factors, which are ratios of related physical quantities expressing the desired units. The derived units are based on SI units, e.g. area is length times width, or in meters. Therefore, the derived unit of area is meter squared. When doing dimensional analysis, problems follow the following steps. First, identify the given, what is given, number one. Then identify the conversion factor that will help you to get the desired unit from the original unit. Okay, so let's say we are given 1 kg. Then they say we want it in grams. So we identify what is given, we're given mass in kgs. Then identify the conversion factor. So you want grams, so you know that 1 kg is equals to 1000 grams. Then set up your equation so that the undesired unit will cancel to give your desired unit. So the equation is 1 kg is equals to 100 grams, 1000 grams. So 1 kg goes to what? So I think maybe let's make it, let's say 10 kgs, so that it makes more sense here. So here we want to know 10 kgs. So basically what it means is we say this is a proportion. So since 10 kg you get more grams, so the 10 goes on top, 10 kgs divided by 1 kg times 1000 grams. So the kgs will cancel each other, so we say 10 times 1000, so we get 10,000 grams. So basically that's how we do it. So identify the given, identify the conversion factor, 1 kg is equal to 1000 grams, then set up your equation so that the desired units will cancel each other. So basically what they're trying to say here is use proportion, then simplify your equation to get the final answer. So let's look at an example. How many hours are in 3 days? So identify the given, we've got 3 days. Identify the conversion unit, you know that 24 hours is equals to 1 day. Then set up the equation, so 3 days times 24 hours divided by 1. Then so days here, We'll cancel days. So it will be 3 times 24. So you get 72 hours. So this is how you do dimensional analysis. So dimensional analysis is basically converting units from the given to the desired unit. Nomenclature of compounds. The cation or caution, depending on the school you went to, the cation is always named first with the name unchanged. The anion, or some say anion. Non-metal is written after the cation modified at the end of the IED. So let's give an example. So hydrogen is not a metal. Lithium, all these, you see, these are the groups. Negative. So what we are saying, if so let's say you have we talked of sodium chloride. So we are saying the cation, this is the cation, metal part, and the non-metal. So this is the normal name is chloride, is chlorine. So because it has formed a compound, we are saying we add the IED, so it will be chloride. So normal name is chlorine, like this, but because we are now naming it to be chloride. So this is the same like for oxygen is oxide, for sulfur is sulfide, nitrogen is nitrite. So it goes on. So we are saying the metal part is unchanged. So we have carbon dioxide, like this. So it means the first part is the metal part, then the other one is the non-metal part. So we are saying carbon, the name is unchanged, then oxygen, but since there are two, it's di means two, so dioxide. So it becomes carbon dioxide. So that's how it is. So this is how you name them. So basically, as you get used to it, it will become your second nature. Okay, then there is transition metals. So transition metals can form more than one ion. Thus, we use a Roman numeral after the metal. So for example, copper, there's copper 1, then there's copper 2, iron 2, and there's iron 3. So you see, so if a metal is a transition metal, they specify which part of it, or which you specify which transition are you referring to. So there's a copper 1, which is the first transition, then copper 2, which is the second transition, which means it can exist as copper 1 or copper 2, and iron 2 and iron 3, as you have illustrated here. So transition metals can form more than one ion. Thus, we use Roman numeral after the metal to specify the metal. So how do they form a charge? It means they are losing electrons to form. So you can lose 1 or 2 electrons, but we will cover it more in the other sections. The Roman numeral denotes the charge and the oxidation state of the transition metal. Don't think too much about this at the moment. The oxidation states, we'll cover it later, but this is just to tell you that transition metal, they are metals that can exist with different charge. So for iron, it can exist as with a +2 charge, as you can see here, or with a +3 charge. So the +3 charge, it is you identify. If I say iron 3, it means I'm referring to the 3+. If I say in iron 2, it means I'm referring to the 2+ state. So that's basically what you should know here. So more notes. Some transition metals have specific Latin names. The nomenclature of the transition metal states that the lower charge ends is OUS, whilst the higher charge is IC, as shown in the next slide. It is important to note that OUS and IEC system is inadequate in some cases, so the Roman numeral is preferred. However, the system is usually commonly used in naming acids. For example, this is sulfuric acid. Sulfuric acid, as you can see here. Then the other one is sulfurous, because this is SO for 2 minus, and the other okay, sorry, 2 minus, okay, there's like that. So this is sulfate, and this is sulfide, if I'm not mistaken. But this is just part of the nomenclature. But normally, if you are referring to metals, we prefer using Roman numerals because they are consistent. But for the other compounds like this sulfuric and sulfurous acids, you can use these ones since they are not transition metals. Okay. So this is something just to add your knowledge. So, for example, instead of using, say, copper 1, you can say cuprous or cuprous, I don't know. Then if it's copper 2, you can say cupric. But I would advise you to stick to these ones. These ones are simpler and they don't confuse you. But if you just want to increase your knowledge, you can try to remember this, but if you stick to this, you are more than fine. You're more than fine. So this was just to show you, just in case you are reading a certain book and they just say cupric, then you know it's copper 2. Okay, let's move on. Compounds between non-metals. Compounds that exist, that consist of a non-metal bonded to a non-metal are commonly known as molecular compounds because the element with the positive oxidation state is written first. In this regard, in order to distinguish the different compounds that can be formed, prefixes are used. For example, there's mono, di, tri, tetra. So these are mono 1, di, 2, tri, 3, tetra, penta, hexa, hepta, octa, nona, deca. So for example, if it's carbon monoxide, it means it's 1 oxygen. So it's mono for 1 oxygen. Then carbon dioxide, it's carbon but with 2 oxygen. Then there's borine trichloride, which means it's borine with 3 chlorides. Then nitrogen pentoxide is 2 nitrogen and 5 oxygen. So this are some of the naming that is done for compounds between non-metals. So let's move on. Binary acids. Although hydrogen fluoride can be named hydrogen fluoride, it is given a different name to emphasize that it is an acid. An acid is substance that dissociates into hydrogen ions and ions in water. Thus, it anions in water. Thus, it is important to include to represent aqueous after acids, as the same compounds can exist as gases. So, if it's a gas, it's hydrogen fluoride. If it's an acid, it's hydrofluoric acid. If it's a gas, it's hydrogen bromide. If it's an acid, it's hydrobromic acid. So the same with hydrogen chloride and hydrochloric acid, then hydrogen sulfide and hydrosulfuric acid. So this aqueous, which means it's in aqueous state. means in water. Then this is gas for gas state. So this is just something to know. So polyatomic ions. So these are some of them. Took it from a certain textbook. It helps you to name them. But the common ones are cyanide. This one, cyanide. You see CN1 minus is cyanide. Then there is sulfate. This one. Then hydroxide. Then nitrate and nitrite. These are quite common. Then this carbonate is very common as well. Then chromate and dichromate are quite common. Then okay, sorry, this one was hydrogen sulfate. Then this is the sulfate, and this is the sulfite. So remember, these are American spellings, but for the British one is sulfate. Sulfate like this. Then the other one will be sulfite. Like this, I think. You can cross-check it in your dictionary. So these are American. So American, they just put an F, but for the British one, we put PH. So something like this. So you can look at them and memorize them. So this is ammonium ion. You can see NH4 plus 1 plus. So these are polyatomic ions. So you can go through them, try to remember them, so that when you see them, you won't. You know, when they say sulfate, you know, phosphate, they are referring to this PO4 3 minus. So that's all for Unit 1, and the next section will be Unit 2.